Welcome again, everyone. Feel free to drop in the chat your name, your role in education. My name is David Porras. I am the head of content at Mathagon, and we're really excited to continue our guest speaker series for the 2021-22 school year. I'm going to give a quick tour of Mathagon and then turn it over to Sunil. You came to hear him, not me. But as you may know, Mathagon is a mathematical playground with best-in-class virtual manipulatives, engaging and interactive courses, and a wide variety of mathematical activities. Mathagon is free for all teachers and students around the world. You can go to mathagon.org. That's where I am on my screen right now to learn more. You can go to Polypad to explore virtual manipulatives. I'm going to show you one super fast example. I'm going to put a square on the screen. I'll copy it a few times just by using the C button on my keyboard and my mouse to move them around. I'll move it over on the screen a little bit. And one of the options at the bottom is to fold net. Oh, it always makes me happy when I fold the net here. And so I can move it around as a 3D object. I can use this slider back and forth to unfold it. I could click unfold to put it into the squares again. Just one super fast taste of all the things that are available on Polypad. You could go to activities. I'm going to leave Polypad here. And under activities, you could explore a timeline of mathematics, of all sorts of wonderful mathematicians and artifacts over the course of history. You could go explore an almanac of interesting numbers that you could scroll through and zoom in and zoom out to find all sorts of fun facts about interesting numbers. Under activities, you can explore a whole host of problems and puzzles. We have a puzzle calendar every December. So if you're not giving us a follow on Twitter, at Mathagon.org on Twitter, every day in December, we post a new puzzle on Twitter. This one was from 2020. Here's one quick example. Place a star in every row, column, and region. And I'm not going to show you the solution, but you could click on it and you could explore the solution. And then finally, you could go to courses and explore an in-depth exploration on a mathematical topic. We have a number of courses available. Finally, by clicking on 4 teachers at the top, you can see a range of options for learning about Mathagon with students. If you click on events and webinars, you can see past webinars that show you kind of a how-to of Polypad and all the tools on Mathagon. You can go to tutorials to see a number of videos of how to use Mathagon in classes with your students. And finally, you can click on lesson plans to see over 100 student explorations, lesson plans, puzzles, games, and teaching ideas. And this you can scroll down just to get a flavor of all what's available on Polypad. And finally, if you filter this on the left, you can just get some tutorial pages on how to use the Polypad tools, an introduction, how to use the algebra tools, fraction tools, and so on. Again, welcome. It's great to have you all here. If you have not already introduced yourself in the chat, please do so we can see who is here. And then I'm going to turn it over to Sunil after a brief introduction. Thank you for the quick tour of Mathagon. I'm honored to introduce Sunil Singh as our speaker this evening. Sunil is an author, storyteller, and a porous math educator. He taught math, physics, and English for 19 years before embarking on a new journey of sharing his passion for math, history, and narrative with people all around the world. He works at Amplify to help build and curate rich storytelling into their K-12 math program, and at Mathagon as a content writer. He's also given a number of workshops, including ones at the Museum of Mathematics in New York and the Royal Conservatory of Music in Toronto. His third book, which just came out, go buy his third book, is titled Chasing Rabbits, A Curious Guide to a Lifetime of Mathematical Wellness, with a foreword by Joe Bowler. Again, it just came out. Go check out his third book. It is my pleasure to welcome Sunil to the Mathagon Guest Speaker Series.
Thank you, David, and thank you, everyone. As I'm just looking through the chat and seeing where everybody are from. Again, Definitely a friend or two people have seen in person. Hi, Michael. We still have to go out for that long-awaited drink. Haven't had a chance in the last couple of years, but we'll definitely do it soon. Definitely recognize some other, we certainly do. I definitely recognize some other numbers, and I like the community aspect every time we do one of these webinars. So, whether there's like 7 people on 70 or whatever, it's still a very, nice community to have. And one of the benefits of tonight's webinar, strangely enough, was that there was no title. It was just like I was going to come and do something October 27th, which actually is my son's birthday, but I knew that. Where I was going to sort of play around with that. But there was no title. And this actually worked out quite well because I've done a lot of webinars in the last couple months in terms of, ideas about math history, storytelling, culturally responsive mathematics, all very important topics. But I've been really, really jonesing to do some math, like actual classroom mathematics on the whiteboard. And so what I'm going to do tonight is like a distillate of what I did at the Museum of Mathematics. I spent the whole day doing arithmetic for K to 12 teachers. So to have the attention span and interest of K to 12 teachers in this very sort of fertile ground of arithmetic, but I'm also going to involve algebra because I think algebra is a really poorly placed, often kind of, like we don't need algebra. So I'm going to try to merge the two so you can see the joy and beauty of those two things and where we need to build the bridges. So I'm going to share my screen, my Jamboard. Can everyone see? Okay, now you can see my Jamboard. Dave, can you get an affirmative? I think I'm seeing it in chat. Okay.
Yes, it looks great.
Okay, super. Thank you. Thank you. You're just never sure, even though it says people can see, you just never know. You don't want to talk for 10 minutes and no one's listening or has seen you. Okay, so a couple things. One, I love Google Jamboard. The laptop I was going to do this webinar is much faster. There's some lag when I do the Jamboard, but it's okay. It's going to be fine. But what I want you to do is I want you to remember, like, okay, where did you start in a particular idea? And I had a goal and I worked backwards. Like there's an idea concept that I want students to get to. But I thought really hard every single time, where should I start? Where should I start so it's the most inclusive, so it creates the most curiosity? And so that's what I really try to do when looking at math ideas. It's not taking like, the straight A to B path, maybe it's like, kind of going off on a side road, an adventure, or maybe coming at it completely differently. So right away, I think I probably have your attention, right? Like, I got 3 unknowns, like I'm starting already, with, algebra. And it's equals to like, keep calm, like that sort of meme of idea of 42, which is the answer to everything. So you're curious, and maybe students are curious too. But I'm not going to start there. But remember where we're gonna cross that point. I'm just looking for there's my trusty pen. This is where I'm going to start. Is it on pen? Yeah, it is. Okay. So 6 times 7. Let's make sure it's on a pen mode. Yeah, it is. And again, I apologize for the lagginess, but I will talk. It's not bad. Okay. This is where I would start. Actually, I shouldn't even put 42. I should just put 6 times 7. Now, that's a math fact, right? And that's good. We want kids to know timetables and math facts. But what I would tell you is that there's a math fact far more important than 6 times 7 for 42. And we're going to come back to this also. I would say I would like kids to know that 2 times 3 times 7 is equal to 42. Because now kids can create their own family of math facts around 42. I've done this with my own kids. I say, pick a number 2, 3, 7. They go, okay, pick 3. Good. Now multiply the other 2 numbers. Well, 2 times 7 is 14. And guess what? Here is maybe kind of, because kids only know the 12 times 12 table. So here's something a little bit out of bounds in terms of math fact, the 42, but you create it if you break it down in terms of its prime factors. So I think 2 times 3 times 7 is a far more important math fact to do. And then later on, kids will always maybe try to break down numbers, composite numbers into their prime factors. So remember where I started, 6 times 7 is 42. So we've done that. Okay, like, okay, there's a little bit more to 6 times 7. In Japan, they don't write 6 times 7. What they would do is write 42 equals. You see what happened? If you give the answer, you now have this inclusive infinite solutions to be offered. Like 6 times 7, you're locked in, and what if a student like, oh, I forgot my times table, oh, I don't know it. Like, it just sets them back, right? Like, it's really tight, that domain of what you want to get out of it. But if I put 42 equals, now it's like, okay, hey, who's got an answer? I got 142 plus 0. Good. You can get infinite answers, right? Infinite answers. And that's really what I'm trying to get to, is like, okay, if we flip it around, then we can invite various ideas about operations and multiplications, and kids can come up with clever ways to build 42. So we got some 42 action happening. And the next thing I would write, believe it or not, I don't think I need this anymore. I'm just going to push that off to the side. Up here, thank you. And I'll go back to my pen. I'm going to write 42. I think our approach to algebra, first of all, it's so delayed. It's compartmentalized in high school. And when we start equations, I would start off with sort of, one equation with 2, 3 unknowns, so these Diophantine equations, because you invite infinite solutions. So again, if I put, hey, and X, Y, and Z, they can be the same number, and have kids come up with any kind of, restrictions or ideas, and you're going to get, hopefully, infinite solutions is the final response. Sure, you get some fun ones on the board, like 42 plus 0 plus 0. Maybe you get some sort of symmetry, going back to, what was that? 14 plus 14 plus 14, right? 3 times 14. Maybe you introduce negative numbers, 42, plus 2, take away. You can introduce lots of things. Again, this is not where I want to get to. So you've got everybody and they're curious, and then you put down this. And again, you can review a little bit about squares, which some kids get introduced to by grades 6, I believe. And before the discussion of a possible solution, just see if you can talk about the key idea here. You see, in the previous case, when the degree was 1, we had so much flexibility. Yeah, we can get some negative numbers out of this. I got lots of solutions. The key idea here is we've lost the negative for the values of input of X, Y, and Z. We've lost it, because when you square a number, it's positive. And I think that's an important thing for kids to go, oh, it's going to be hard now. And you go, yeah, it's going to be hard. Do you think it's impossible? And now kids are, rubbing their forehead, and, they're trying to remember their squares, right? And even if they don't add up to 42, they're practicing, 1 squared is 1, 0 squared is 0. Is there some number squared going to be 42? No, it's probably going to be irrational. It's like, that's a fun conversation to have. And now kids are going, maybe, to you, or is there a solution? They go, there is. And finally, hopefully it comes out where it's like 5 squared plus 4 squared plus 1 squared will give you 42. So there is a solution for 42. And kids can verify it, whether you want to go explicit, 5 times 5 is 25, add it up, but you've got everybody still. You've got everybody. So then you go, you know what, can we do one more level? And kids are going, what do you mean by one more level? So I'm just going to go up here. I don't want to go to the next slide. I'm going to cube stuff. Now, again, it shouldn't be a stretch to go into cubes, even if they haven't done it, because it's the idea, okay, you know what, something cubed is it's a base, right? We don't know what the base is, but you know, if we pick 5 times 5 times 5 is 125. Whoa, it really explodes, right? And you get into that excitement with the kids, like, hey, it's exploding, it's going to crazy. You know, you try 3 times 3 times 3 is 27. And kids in a very disarming fashion are learning their cubes. But here's an important point which can come out. We introduce getting our negatives back. So especially if it's, you know, further up middle school or high school, kids should know that if you cube something with a base which is negative, it's going to stay negative. And you can, you know, -4 cubed is -4 times -4 times -4. It gives you 64, and the actual final answer is -64. And have this discussion going, isn't that good? We got our negatives back. And they go, yeah, I think so. And then you go, okay, go. I'll give you half an hour, and the person who gets the answer, actually, I'll give you an hour or whatever remaining class time is left, and whoever gets the answer, I'll sign a check for $1 million. And now the kids go, you're not going to give us $1 million because there's no solution. I go, no, there's no solution. There is a solution, but if you have a phone, can you put it down? Because I don't want you looking it up. So that's my way of getting kids to practice their cubes for whatever amount of time. Because as some of you are familiar with this problem, there is a solution. And it was the last solution to the sum of cubes problem, 42, which I think was 2017, I believe, and we used a lot of, you know, supercomputers and stuff. And there it is. 42 is a very skinny number, right? And to get 42 with sum of cubes, you got to use these ginormous, I would use that language. You got to use these ginormous bases and cube them. And when all is shaken out, believe it or not, those 3 numbers add to that very small 42. I like problems which introduce large numbers. It's what got me into mathematics. When I was a 13-year-old kid, looked at Guinness World Book of Records as the largest number ever used in a math problem or proof, which is Graham's number at the time. It was like a small little detail. But that was a turning point for me. Like, I don't even understand Graham's number. I don't even understand the arrow notation. And it's still challenging now as an adult. But that's how I got hooked. Large numbers. And this large number popped up in the story. And look where, this is where I wanted to get to. But how would I present this to like even like middle school kids? I had to start with 6 times 7 equals 42. So yes, that was that's narrative, right? But narrative pays dividends down the road. Okay, so some of you, I don't know if you've seen my webinars before, but maybe you know what's going on. Again, I could present this question probably in an elementary class. And the first thing, I would just even put the visual up.
So what do you want to drink?
Oh, sorry, it's okay. I just heard some background vocals. I would just leave the visual up. And I would go ask kids, what math question do you think I'm going to ask? Like, try to be as inclusive as possible. Don't even skip that step. Don't go into your problem. Just put the visual up. And maybe kids might go, well, how many steps are there? I go, that's a pretty good question. Can we answer it? Sure, we count them. 1, 2, 3, 4, 5, 6, 7, 8. And you write that down. There are 8 steps. And the question you ask is, how many ways are there to get up these 8 steps if you're allowed to take 1 or 2 steps only? So you're allowed to take 1 step or 2 steps. You can take a jump of 2 or jump of 1. And you can put down an example. You can have 4 hops of 2. It's always got to add up to 8. You can have a pretty kind of pedestrian 1, 1, 1, and then maybe a hop of 2 at the end. Still adds up to 8, but maybe hop to 2 at the beginning, which is a different way to get up the steps, right? What I'm waiting for is a kid question, because as an adult, I don't know if I would ask this, but I bet you a kid's going to go, can we go backwards? And you go, before I say yes, what happens if you go backwards? What kind of is that, and hopefully they say something about subtraction or integers. And then hopefully you keep going there, go, oh, okay, well, if I'm allowed to go -2, then +3, then -1, then plus, is there going to be like lots of solutions? And hopefully the word infinite comes up again. That's a very important word for kids to learn early on, to understand some basic concept of infinite, right? It's a mind-blowing thing, but have it come up in just conversation. And it came up because, and of course, in this question, you have to always be moving forwards. So just for the sake of time, normally I would workshop this, and I did this where high school teachers, they're going into combinatorics and all that kind of stuff, which is fun. I love hearing that conversation. It's good. It's good. But I only put this question on because sometimes we bypass the simplest solution. The simplest solution. And for me, a key strategy for this is try a simpler problem or try baby steps. It's a very important strategy in mathematics. It comes up quite often. And it's also very philosophically important because kids are not answering the question directly. They're saying, you know what, can I get back to that one later? I'm going to work on a smaller problem. That gulf between the problem you pose to them and the confidence to veer away for a little bit to start somewhere else is a mathematical, you're thinking like a mathematician. And that to me is good enough already. So if we start with baby steps, when one step is only one way to do it, right? You take one step, total is 1. And I love it. There's trivial solutions at the beginning, right? So 1, 1, and 2, right? That's the only way to get up when there's 2 steps. So it's 2. And again, maybe it gets interesting at 3. I don't know. Does it? You get 2, 1, and 1, 2. Those are 3 different ways. There's no other way to get up 3 steps than with those. And this is a good time to just go have kids even guess. Maybe they're going to say 4. Maybe they're going to say it's going to be different, but have that discussion. That's sort of a little bit of, back and forth before you continue. And of course, if you go through all the solutions, I'm not going to put the parentheses because it's just, actually I will. And maybe there's a systematic way to do it too. Like, 1, 1, 2, so I don't miss my 2s. I'm just pushing it to the end. Should have put this up front. There you go, like that. And I think I'm missing, 2, 2. So there's 5 ways. Oh, it's not linear. So now you got their curiosity going, okay, I bet you it's going to change maybe by something else. Well, have kids find out. It turns out to be 8. It turns out to be 8. And a lot of, some of you are going to go, that's Fibonacci. Yeah, that is the Fibonacci sequence in terms of, adding the 2 previous numbers and getting that next result. So if you add 8 and 5, you get 13. You add 13 and 8, you get 21. And you add 21, 13, you get 34, which is the total for 8 steps. Now, I don't know if you know this, but it doesn't matter what 2 numbers you add to get the golden ratio. So if I was to even go like, -3 and 6, those are my seed numbers. The next one is going to be add the previous 2, it's going to be 3. Add the previous 2, it's going to be 9. Add the previous 2, it's going to be 12, 21, 33, etc. And eventually, if you have enough data set and you divide one number by the previous one, you're going to get that golden ratio of 1.61. Doesn't matter what your seed numbers are. Right? Keep having these circular conversations around every single topic that you teach. Make it seem like there's a storyboard around it all the time with anecdotes and things like that. So, but there's a curveball here. It was not Fibonacci who was the first person who discovered this. It was Hemachandra, a Sanskrit poet from India about 100 years earlier, who was studying Sanskrit poetry. And in Sanskrit poetry, you have these 2 kind of vowels, lagu and guru. Lagu is like sort of 1 beat and guru is 2 beats. Takes up 1 space, take up 2 spaces, walk up a set of stairs, whether 1 step or 2 steps. You're going to get the exact same answers as Hemachandra got. So you not only do you get this really wonderful problem where you have to have a mathematical sort of strategy starting from the beginning, but you also have a curveball at the end where, oh, I thought it was Fibonacci. No, it's Sanskrit poetry. And maybe there's a couple of kids in your class who have an interest in language humanities and are maybe budding poets. Maybe they delve into learning more about, some of the poetry or ideas in Indian Sanskrit poetry and things like that, right? You're trying to create all these sort of little mini micro rabbit holes all the time. So we're not done here. We're not done here. We're not done here. So I'll just use G and L to keep it specific to Sanskrit poetry. Now, G is Guru, the long, and L is Lagu, is short. So this is going to be a different question. So now we want to make 4-syllable poems, right? As long as it's got 4 syllables, it's fine, right? Just 4 syllables, but it's got to have 4. I don't care if they're all G's or all L's, but it's got to be 4. So again, for the sake of time, normally I'd have you think about it, start plotting, putting your answers down, but I'm going to, get us going, and I'm going to put like off to the extreme. And I think that probably gives you an idea of where this probably went, did go hundreds of years ago, right? So I got remember, there was a lag here. I apologize. Now it looks like something else. Okay. You know what I'm talking about. So as long as it's got 4 letters, it's a kind of a poem. So I'm partitioning this now, and maybe again, you have an idea what's going to happen. So if we have a poem which has only 1 guru, then you can see we can slot that in 4 different ways. And now I'm sure, especially the high school teachers, you know exactly what's going on. And I'm just going to go to the other. So just for symmetry purposes, L, G, 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 L, G, G. Now I know my ABCs, maybe, or my LGs. And got a total of 1, got a total of 4, got a total of 4, got a total of 1. And as some of you already know, it's going to be 6 for having 2 gurus and 2 lagus. And 1, 4, 6, 4, 1. I think especially middle school teachers and up, even maybe some elementary teachers, this is definitely, a row from Pascal's Triangle. This is a row from Pascal's Triangle. And you can play with Pascal's Triangle by actually using some history from, another country, from another time, in terms of some of the mathematical origins, which other, cultures and civilizations and races obviously intersected with. So there it is. There is the 4th row of Pascal's Triangle. And, Pascal, I believe, he suffered from really bad migraines. I could have gotten the story wrong, and when he had these migraines, they're really intense. As you know, eventually, if you have medication around, your own brain will release some endorphins just to, try to keep the pain at bay. So he actually had a lot of his mathematical epiphanies when he was having his most excruciating headaches, because he had these endorphins released, and maybe it creates some sort of lucidity, maybe a little bit of psychedelic high. So that's where, and I'm pretty sure that he documented that, or if it was, some mathematician definitely had that. But Pascal was the 5th mathematician to discover this triangle. About 100 years earlier, Tartaglia, the Italian mathematician, he discovered it. And then before him was Omar Khayyam, who, according to Keith Devlin, was a far better mathematician than poet. Most people know him as a poet. He said he was an okay poet, but he was an unheralded mathematician. And then if we go back before that, I believe, I could be wrong, I do mess up my history sometimes, as Yang Hui from China. And lastly, the first person was another Sanskrit poet, Pingala, about 200-300 CE, current era, where he played again with Sanskrit poetry, and he discovered the relationships, which we later known as Pascal's Triangle. And I'm going to share something with Pascal's Triangle, which I'm pretty sure very few of you know, because I've seen high school teachers sort of say, I didn't learn that. I did. I was just part of our curriculum. And so you can see I've drawn Pascal's triangle, I have it, the standard one, and then I've kind of got a blank one sitting at its apex. You go, why are you doing that, Sunil? Why are you doing anything? Well, let me continue the ones, right? Because the ones do get angled off in that direction like that. So that shouldn't be too, and there's a whole bunch of zeros this way, right? There's nothing here. This is like the forbidden zone. Was that like in Planet of the Apes? Am I dating myself? Yeah. Sometimes I forget I have an audience and I just sort of amuse myself. So you think, okay, there's nothing going on. You're right, but let's continue the zeros here in the 0th row. And if we follow the same rule that 3 plus 3 gives us the number right below it, the same thing's going to apply. But to get this 0, we need a -1. 1 plus -1 is 0. This needs a +1. This needs a -1, +1, -1, +1, -1, +1, -1. And it goes out forever. This is an infinite geometric expansion, binomial expansion, if you have a negative exponent. And I'll just do one more and you can explore this. Try to Google it. Try to Google outside expansion of Pascal's triangle. It's really hard to find. So to get -1, I need -2. To get +1, I need +3. And these will be the actual exponents in this infinite expansion of that expression. So, one more story to add on. Wasn't, it's fun. I think it's fun. Okay, it's October. It's the end of October. So I'm a firm believer in getting kids to think about algebra as early as possible, especially if there's a bridge of some sort of arithmetic. And I was playing around with the calendar a couple of years ago, and I go, you know what? A calendar is super rich because kids have calendars on their fridges. They know about tomorrow. They know about today. They know about yesterday, next week, last week. And you'll understand what I mean by why we can sort of mine that to really have kids really explore the calendar algebra. So what I used to tell kids is, okay, I want you to add up 4 numbers that make a square on a calendar. So for example, a student might have those 4 numbers. Okay. It's got to make a square. Okay, there's other rules and shapes you can make, but that's the one I started off with. And I used to tell students, okay, add up your 4 numbers, tell me what they are, and I'll tell you your 4 dates in a second or 2. And, in this particular example, it'd be 27, 40, 68. And I would be, okay, yes, I can see the answers, but I'd be able to rattle off 13, 14, 20, 21 like that. And of course, when you can do that, kids are going to go, how'd you do that? Is it memory? Is this trick? You go, and you do a whole bunch. And then kids, I go, do you want to know? They go, yeah. So it's got to come from them, not from me. If they don't want to know, fine, I'll do something else. Maybe I'll juggle. But every kid's going to go, okay, show me how to do it. I go, okay. So I go, I don't know your date, do I? Right? I don't know what your dates are. I had no idea. So if I don't know something, what do you want to call it? And at this point, kids are probably familiar with unknowns and maybe they go X. Right? And I go, what about the day after? And I actually don't mind a answer I'm not looking for because it creates discussion. I don't want to hear X plus 1 right away, believe it or not. I don't. I'd rather hear Y. And I go, good, I don't know. I have no idea what that date is either. So let's call it Y. And then maybe kids down here will go, okay, well, that's got to be maybe another letter, W, right? And this has got to be, that's okay because they can't be the same letter. I have no issue with that. That's a good discussion point, but I go, oh, W plus X plus Y plus Z. I could never do that. I had no clue. So I'll just choose another set of 4. And I go, but the day after is just one more day after. It's one more day after X. And as long as it takes, get it out. Have it come from the students where they'll go, Well, that's x plus 1. And I go, does everybody get that? That the day after x is x plus 1? Because if that day was 4, the next day has to be 4 plus 1. Be explicit. Do not be more explicit than you have to. Bore them with how explicit you are, because it'll pay dividends later. And then ask who knows this date. And I bet you half the hands go up. And I go, are you sure? Because this one's, is it x plus 3, 2? You know, it's a week later, so it's x plus 7. And this is x plus 8. And so what I tell the kids is, you know what I'm doing? I am adding all 4 of those unknown dates in my head. That's a 7, sorry. And I've run out of room. And I go, well, how many x's do I have? These are like terms, expression of like terms. 1x plus another x plus another, that's 4x. And if I total up everything else, that's 16. I have made a little equation of that little rule about calendar dates and making a square. And why am I doing it so fast? Because I'm subtracting 16 divided by 4, subtracting 16 divided by 4. I've practiced that over and over and over and over again. I could divide by 4 and then, and that creates a discussion about why it's always important to get rid of the constant in front of your variable last. I'm not saying you can't do it if you don't do it last, but you might get into fractions. So that's why I create that rhythm. Subtract 16 divided by 4, subtract 16 divided by 4. And then kids can maybe try making their own shapes, make their own shapes. But you create, and here's a point where you go, did I have to make X the first date? And they go, yeah. I go, really? And then maybe you go, I'm going to make this X. So what's this one after? And they go, well, oh, that's X plus 1. Good. What's the week before? And again, they've got this narrative about week before, and that's why hopefully they'll come easy and go, oh yeah, that's 7 days before, that's X minus 7. And this is only 6 days before. And when your kids are going to be excited to test that equation, which doesn't look like the x plus 1, x plus 2, x plus 7 plus x plus 8, and still get the right dates. That flexibility of assigning an unknown and making sure that everything around it corresponds to that, that's a super important idea in algebra. That comfort zone of, okay, I'm going to give that, but I can make everything relative to it. And there's more to this too. So I tell kids, okay, you have a dice, and the 5 looks like this, the 5 pips. Oh, by the way, just as an aside, because I've got, you tell stories, right? Casino dice, they have sharp corners, and they have the pips. There's no divot, they're flat. Casino dice. And there's 2 reasons for that. Well, sharp corners means the dice is going to roll less, and rolling less means less time wasting those seconds, microseconds, whatever, and those dice get back in the hands of the person who's rolling them, because the casino makes money basically on law of large numbers, and it's just going to keep, so every second counts. And then the pips, which are filled in, that's because the 6 technically is the lightest side. In normal household dice that you play with Monopoly or other game, this is the lightest side, and you can't have any kind of deviation from the things you're trying to get if you're a casino. It's because over thousands of rolls, the lightest side will appear, and that's going to affect getting 7s and things like that. That's my aside. So going back to the 5, pick 5 dates which make that sort of particular orientation, and do the algebra. I'm not interested in the algebra. I'm not interested in the actual solution. There's something very cool which comes up in terms of divisibility, and again, where you're going to put the x. See, strategically, you should put x here, right in the center. And then you've got symmetry above and below. This is going to be x minus 8. This is going to be x minus 6. This is going to be x plus 6. this is going to be x plus 8. You can do it to show it, but again, there's some intuition that kids can see that these terms and those calendar dates are going to cancel out in terms of the numbers, plus 8, minus 6, plus 6. I can do it, but you're going to be left with 5x equals the total. To need that bottom there, which means that if you pick 5 dates in this shape, it's always going to be divisible by 5. And maybe you can talk about the divisibility rules of 5, which aren't very interesting, ending in 0 and 5. Maybe that becomes your portal and talking about divisibility rules for other numbers. You're always connecting these threads, right? Each thread, maybe sometimes the thread just ends, or maybe it goes on. And it's that shock and awe early on. And I know I'm going to miss saying this. I'm going to say it now with 15 minutes left. Everything I've done so far, there's 3 stages of learning, according to Alfred North Whitehead in his 1929 book, Aims of Education. And I'm going to go backwards because the first 2 we tend to very well. The last stage of learning is called adulthood, which is called generalization. So everything you've learned, you can generalize things, you can sort of, make macro sort of pictures. We do that, right? We're good at that. The one before is precision. And please focus on mathematics. And that occurs in youth. And of course, think about how much precision we want from our kids in terms of, their arithmetic, their algebra. You can't get questions right if you make one mistake in algebra. We're all going to make it, but you have to attend to that precision if you want to get the final answer. Okay, we're all good. The first stage, you can't bypass this, but we've bypassed it for 100 years. The first stage of learning is called romance. Kids have to fall in love with mathematics. If they don't, we can have a pretty good guarantee. We know how it's going to turn out. We see how it turns out. Worst case scenario, you get math anxiety, alienation, trauma. Less serious, you get boredom. But we didn't attend to romance. And as I've said, I'd rather err on the side of over romanticizing mathematics than under romanticizing. Okay. So I've got time for this problem. And I know 1 or 2 of you are familiar with it. Unfortunately, Peter Harrison, who created Cows in the Classroom, this site unfortunately got taken down just in terms of domain, and it's really sad. And Peter Harrison is the person who I talk most about in my book, Cows in the Person, Cows in the Classroom, Sunil. And I could spend days on cows, and I've just chosen this one problem. And this is not where he starts. He starts with simple ideas, which you can do in 3rd and 4th grade. And you can actually go right into university topics of eigenvectors, just doing cows and this template. So remember when I showed the stairs, like, again, just show a visual. Don't even put any instructions on. Have kids absorb, like, okay, that's a lot of unknowns. And that's disarming on itself. And ask them, do you want to know the relationship? They go, of course I do. Well, the lowercase letters are bridges. And the best way is to do an example. And the large letters are the number of cows in the field. Okay. And we don't want to get messy, but these are whole number cows, right? Or just, Peter always made jokes about that. We have to have whole, these sort of whole number solutions. So these represent cows. So for example, if this was 2 and this was 3, then the bridge, in this particular case, the bridge can usually represent a lot of different things, but in this case, it represents a sum of adjacent fields. That's easy, single digit. And this is why I consider this to be the greatest K-12 math problem, because kindergarten, grade 1 kids can do it. I haven't even explained what we have to do. A certain sophistication occurs in middle school where you can talk about other things. And in high school, there's an actual algebra solution, which I'm going to show you tonight. But I want you to think about this problem sitting in a 1st grade class, because here's the question. You've got to put single digit numbers in. So 1 to 9, most kids by 1st grade are pretty, they can count to 10. And maybe they've done some single digit addition. So that's good too. So they got to put the numbers 1 to 9 into this puzzle. So it fits. It feels like a kind of a Sudoku-ish kind of problem, but it's got a little bit more weirdness and fantasy realm with cows and stuff, right? That's why it appeals to that elementary grade. So brute force, that's a wonderful strategy for kids to eventually exhaust because they want to exhaust it, not because you're telling them, hey, you should stop doing brute force. If they want to do brute force till grade 12, do it, because they have not, the elegance part hasn't been needed. It has to be needed from them. So brute force, kids can be jamming in numbers early and they can get half the solution, half of it right. And I had a teacher, elementary teacher, instead of using paper and pencil, she had towers of Unifix cubes, 1 through 9, so kids could slide around very quickly without, wasting paper. That was brilliant. So first grade, brute force, go for it. Well, maybe what about in like middle grades, where now you can still use brute force, but now you can talk about evens and odds, right? Just put your answer at even and odds. If you had an even number here and an even number here, then the bridge has to be even, right? Or you can talk about what numbers can't the bridge be, because you can't use the numbers more than once. You can't repeat them. I don't think I said that. You can't repeat them. So you can't use 1 more than once or 2 more than once. And you can't have a bridge number of 2, and the kids will tell you, because the only numbers are add to 2. Well, you can't have 0 cows, and you can have 1 and 1, but you can't duplicate. So you can talk about the restrictions, and you can talk about even and odds. And then lastly, you get to high school. Lastly, high school, or maybe even middle school. So I'm going to give you the elegant solution that I want you to think you can do. So this is, have fun, go, you know what, let's just add up all the unknowns in alphabetical order. So A plus B, and again, psychologically, I think this is so rewarding. 8 unknowns, right? 8 unknowns. And I don't know the total yet, because one of the numbers will be omitted. Remember, we're not using all 9. So and we can do off to the side, well, what's 1 to 9? Well, 1 to 9, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 is 45. It's a triangle number. Maybe you go off in a little rabbit hole there. But I don't have time to do that. A plus B plus C plus D plus W plus X plus Y plus Z, right? That's a lot of stuff going on. And now you start to ask kids to look back and ask them, hey, can someone tell me what A plus B equals? Like, if field A plus field B, what does it have to equal? And hopefully the kids can see it has to equal X, right? That substitution, that relationship is very important. C plus D. Hey, now there's some, it's Z. And now I've got rid of my uppercase letters. And you know what I'm going to do is I'm going to put things in a little bit of order and organization. I'm going to put brackets, and there is another X plus Z here, right? It doesn't matter which way you add numbers. You can prove it to kids. It doesn't matter 2 plus 3 plus 4 plus 6, 6 plus 4 plus 3 plus 2. It doesn't make a difference. So I'm going to go, oh, there's another X plus Z. I'm getting excited, right? You got to be excited when you're doing this. And then we've got this W plus Y. Whoa, 2 things which are identical. And you go, this one's like the odd one, like the third wheel. And allow pause to, and have go tell kids, I want you to focus on W plus Y. I want it to be part of this X plus Y family. Well, there's W and there's Y, and W is A plus D, and Y is B plus C. Whoa, A plus B plus C plus D. A plus B plus C plus D, that's what W plus Y is. But we know that that is X plus C. So we actually have 3 of those X plus C terms. Look, if someone just came in now, they'd probably be thinking I'm doing a grade 11 algebra problem. I'm not. This is middle school in terms of thinking and the attention and the interest. So let's finish it. So we've got 3 of those X plus Zs. I keep forgetting if I'm American or Canadian. And I put that line through it too. This becomes a discussion point. That's the elegance of algebra. That our solution has to be divisible by 3. Has to be. And so now you can ask kids, remember, it's not going to be 45. It's going to be numbers less than 45. And those numbers better be divisible by 3. And then hopefully you come up with 42, 39, 36. Try those. You know, let's just pop one in. Let's pop in 39. Divide both sides by 3. You've got this much simpler relationship of X plus Z equals 13. And keep in mind that these numbers have to be unique. You can't repeat them. So you don't have, not that you can repeat in this case, but whatever numbers we use, we also have to have other numbers being used too. So, eventually, you're going to get, 9 and 4, and you'll get 7 and 6 for W and Y, and you'll get the fields of the cows, and you've bypassed the brute force solution. But it's important when you showcase mathematics, especially with algebra, that you pair it with brute force, and you don't denigrate brute force. You show it's a very valid, important way to appreciate the elegance of algebra, right? You've got to be inclusive in your answers. You've got to be inclusive in the story of mathematics. And, for me, where the good stuff is, the messy middle, is that bridge, arithmetic algebra. As we're crossing that bridge, as we're crossing that delta to get to the land of algebra, which I, personally find to be very beautiful, we want to get all our students there. So that's my presentation for Mathagon, a little pop-up algebra and arithmetic. And I will stop sharing my screen.
Wow, that was spectacular. Yeah, round of applause, big emojis in the chat. I'm gonna put a link in the chat for folks in the States who should go buy that book right now. Sunil did not ask me to put a plug in there, but
No.
all the amazing, joyful, curious, inclusive math that was shared tonight, that is a long Amazon link. I hope it works, but it's called Chasing Rabbits. Maybe there are other independent booksellers near you that you could buy it from as well. But I was, as I was taking notes, I kept hearing and writing the word inclusive and storytelling and curiosity and infinite solutions, and what fabulous ideals for us to implement into our math classroom. So I got some things to do tomorrow in my 7th grade classes, which I'm excited about. So that was really
and I think that our enthusiasm as teachers, again, if you walked into a classroom, you saw all those unknowns, which class am I in? And it's very important that the presentation is very disarming. It's very silly, because if kids see 8 unknowns in 6th grade, I mean, by the time they get to high school, like 2, 3, like I know what to do with it. I know how to play with it. And then you highlight the key points, and maybe is that something we can collectively rally around, that was it worth it to get this divisibly by 3? Like, wasn't that a nice thing which popped out? And these are other things that you will look for in your algebra toolbox later on. And if we wait sometimes way too long, kids have built up some anxiety about it and stuff. But for me to build a confidence of arithmetic and to get to algebra, it's, and I'm sure I'm preaching to the choir and to the people who are listening and watching tonight. And I hope you try. And a lot of these ideas, and not just I go into far more detail in the book in terms of problems like this. There's a whole chapter devoted to doing things silly in terms of looking at problems differently. And you get a better idea of Peter Harrison, what a remarkable educator he was and what a huge influence he was on my life. So yeah, that's the way I will end it tonight.
Well, awesome. Thank you again. It was really a treat. I got a whole lot out of it, and I know that folks did as well.